Blagoje, I gave you the presentation. I didn't. So Blagoje did his PhD at the University of Brussels and now postdoc in Zurich. And today he will tell us about Barry phases, right? Or,
do you remember the title?
is
Barry
it that?
phases of boundary gravitons.
Okay.
Okay, so here it is. Good, thanks for the introduction. So hello everyone. Before I start, I'd like to thank indeed the organizers and in particular Laura Donnet for giving me the opportunity to speak here today. It's a pleasure to be in Harvard and I hope you will enjoy my presentation. So as announced, I'll be talking about, oh yes, sure, the pointer goes. So I'll be talking about various phases of boundary gravitons. Let me start with a brief motivation. It has long been known that gravitation has interesting asymptotic symmetries. For example, three-dimensional gravity on anti-de Sitter backgrounds has an asymptotic zero symmetry, while asymptotically flat spacetimes have an infinite-dimensional symmetry group, which is known today as the Bondi-Messner-Sachs group, or BMS group for short. Now at this stage, if some of you don't know exactly what asymptotic symmetries are, don't worry. Just think of them as the symmetries of spacetime that are seen by observers who are located very far away from all sources of the gravitational field. Now in practice, asymptotic symmetries are really diffeomorphisms of spacetime that preserve certain fall-off conditions of the metric, and so in particular, they act on the spacetime metric itself. This action then leads to a notion of boundary gravitons, which are defined as follows. By definition, given a certain background metric, the set of boundary gravitons that surround it is the set of all metrics that can be obtained by acting on that background with all possible asymptotic symmetry transformations. Now, the common lore in the literature is that asymptotic symmetries are genuine physical symmetries of nature. If this is so, then there should be certain observable quantities associated with boundary gravitons. And indeed, a great deal of the literature in the last few years has been concerned with such observable quantities, especially in relation to self-theorems and the memory effect. But today, I want to describe one kind of observable that seems not to have been studied until now. Namely, I will argue that when one performs a loop in the space of metrics that belong to a given set of boundary gravitons, the wave function of the system typically tends to pick up a Barry phase. Equivalently, such Barry phases arise from performing loops in a set of reference frames which are related to one another by asymptotic symmetry transformations. So those are the observables I'd like to describe today. But before I actually tell you how one can evaluate them, it's worth asking what we should expect from those Barry phases. And, well, to tell you what one should expect, I can actually anticipate the result by telling you that what we're going to find in the end will in fact provide a gravitational generalization of a phenomenon that has been known for about a century by now, namely Thomas precession. So let me just briefly remind you what Thomas precession is about. Suppose that you have a particle represented here by the red dots, and suppose that this particle follows a circular trajectory. For example, think of an electron which is orbiting around an atomic nucleus. Suppose also that the particle has spin, which is represented here by this red arrow. Then, what Thomas showed back in the 20s is that as the particle orbits around the nucleus, its spin vector precesses. And the effect of this precession is that after completing one orbit around the nucleus, the spin vector, or the spin of the particle, has actually rotated by a small angle. And in fact, the value of that angle is now displayed here. So in this formula, S is the spin of the electron, and lambda is its rapidity along this trajectory. As you can see, I'm calling this angle B, because in fact this angle is a Barry phase. So another way to phrase the question that I'm asking today is the following. It turns out that in order to compute this Barry phase, all you really need to know is Poincare symmetry. In fact, specifically, all you need to know is some properties of Lorentz transformations. But in that sense, we are more powerful than what Thomas knew, because Thomas only knew about isometries. But we know about asymptotic symmetries, and in particular, about BMS symmetry. So the question I'm going to ask is, what would be the result of Thomas precession, and perhaps can we generalize Thomas precession by thinking of BMS transformations instead of just Poincare transformations? So with this motivation in mind, here's the plan of the talk. In the first section, I'll review in general terms how Barry phases appear in group representations. Then the second section will be a brief technical interlude on some aspects of the Virasoro group. And then in the third section, I will actually embed this Virasoro group as part of an asymptotic BMS symmetry group, and then display the corresponding formula for Barry phases. So to introduce first Berry phases, suppose we're given a certain quantum mechanical system that depends on a certain set of continuous external parameters that we can tune at will. Those parameters are coordinates in parameter space, which is some manifold M, and the Hamiltonian of the system is generally parameter dependent. So are, of course, the eigenvalues and eigenvectors of the Hamiltonian. Here, I'm focusing on one specific eigenvalue, which I'm calling E and assuming to be isolated and non-dependent. Now, the question we're going to address is, what happens when those parameters start varying in time? This means that we're following a certain path gamma in parameter space, and it effectively makes the Hamiltonian of the system time-dependent. The problem then is to solve the Schrödinger equation with such a time-dependent Hamiltonian. Here, for definiteness, I'm assuming that the initial wave function of the system is in fact an eigenvector of the Hamiltonian at the corresponding points in parameter space. Now, thanks to the assumption of adiabaticity, meaning that we vary the parameters very, very slowly, the adiabatic theorem actually ensures that, given this initial condition, at any later time t, the wave function of the system is actually proportional to an eigenstate of the Hamiltonian at the corresponding points in parameter space.
Pardon me, when you say you vary them slowly, what's the comparison timescale?
Right, so typically, if there's an energy gap, the energy gap tells you the timescale that you're supposed to be slower than. So, thanks to the adiabatic theorem, you know that this is true, and the only thing you need to fix is the phase that's actually a proportionality factor here on the right. Now, since the right-hand side involves an eigenstate of the Hamiltonian, it's pretty obvious that the phase is going to involve its energy, but crucially, there's also a second contribution here, which you can write schematically as the integral over the path gamma in parameter space of the one form A, which happens to take the form displayed here. This one form is in fact known as a Berry connection. Now, the reason the Berry connection is important is because when you consider a closed path in parameter space, meaning one whose endpoint coincides with its starting point, this contribution here becomes actually a holonomy of the Berry connection, and that holonomy is known as a Berry phase. So it's abstractly given by the formula written here. And in principle, such Berry phases are observable quantities in quantum mechanical systems. So Berry phases are the observables I want to consider today, but specifically, I want to consider them in the context of group representations. So suppose you're given a certain symmetry group with the algebra I denote by this letter, and let's assume that the group contains time translations, meaning that there's an element x in the algebra, such that exponentials of x are interpreted as time translations. Suppose also we're given a certain unitary representation of the symmetry group. This representation acts in a Hilbert space, which you can think of as the space of states of a quantum mechanical system whose evolution operator is just the representation of time translations. Equivalently, you can write this evolution operator as an exponential, where here on the right-hand side, lowercase u is the Lie algebra representation that corresponds to uppercase u by differentiation. Everything I just said on this slide is so far completely trivial. But, oh no, sorry, and indeed, the next trivial thing is to note that this means that there's a Hamiltonian operator. So this is completely trivial. But now comes the key insight that's going to lead all the rest of the talk, basically. The key insight is that everything I just said, in fact, relies on an arbitrary choice of reference frame. To explain this, suppose that we have two observers, called Alice and Bob, who are looking at this system. And let's assume that Bob is related to Alice by a change of reference frame F, which is a certain element of the symmetry group. If then Alice observes the Hamiltonian H written here, the Hamiltonian seen by Bob will instead take the form written here. And as you can see, this is in general very different from the initial Hamiltonian seen by Bob. So we readily conclude that whenever we have a symmetry group that contains time translations and a unitary representation thereof, we readily obtain an entire family of Hamiltonian operators which are labeled parametrically by the points in the group manifold. In other words, from the perspective of quantum mechanics, you can now think of the group manifold itself as a kind of space of parameters. And it's natural then to inquire what happens when those parameters vary adiabatically and in a cyclic way. So to answer this, let's pick an eigenstate of Alice's Hamiltonian and a certain closed path in the group manifold. And if then you look back at the formula I wrote earlier for Berry phases, you just plug this data inside, what you end up finding is this compact formula for the Berry phase in a group representation. Now, the most important ingredient in this formula is the argument of the Lie algebra representation u on the right-hand side. That argument is f inverse multiplying the time derivative of f dot. And in mathematics, it's known as the Mora-Cartan form of the group G. So what this formula is telling you is that if you know the Mora-Cartan form of a group, well, then you know it's Berry phases. You just have to plug it here and compute Berry phases. And indeed, the second section of the talk will deal with specifically the Morag-Cartan form of the Virasoro group. But at this point, let me just make one conceptual comment. You can think of these very phases arising from the fact that you've taken a particle represented whose wave function is the wave function phi, and then you've acted on that particle with a cyclic family of changes of reference frames belonging to this group G. And the statement here is that as you do this, the particle picks up a Berry phase. So another way to phrase the question of the talk is really what happens when these changes of reference frames are in fact asymptotic symmetry transformations. And as I announced, I will answer this question, at least in part, in the third section of the talk. But first, let me now turn to a brief technical section which will deal with the Morag-Cartan form of the Virasoro group. Now, as I said, the reason I want to do this is that Virasoro will really be part of the BMS group. But the second reason is also that, well, I need to introduce the transformations that are used in BMS. Now, Virasoro is a centrally extended group, so let's start by dealing, for simplicity, with its centerless version, which is just dFs1. dFs1 is the group of diffeomorphisms of the circle, and you can think of it as one half of the conformal group of a two-dimensional Lorentzian cylinder. Its elements are functions f that depend on an angular coordinate phi, and they're such that they have winding number 1 on the circle, and they preserve the circle's orientation. The group operation is by definition given by the composition of diffeomorphisms, and the correspondingly algebra consists of vector fields on the circle. In CFT language, you might know this algebra under the name of the width algebra, generated by Fourier mode vector fields of this form. So, if our goal is to compute the Morag-Cartan form in dFs1, the first thing we need to do is to pick a certain path in the group manifold. Now, in the case at hand, such a path is really a function f that depends on a time parameter t along the path, and also on an angular coordinate phi along the circle. And then, by definition, the Morag-Cartan form is f inverse multiplying f dot, but here multiplication is really composition, so if you use the chain rule, what you end up finding is that this Morag-Cartan form is in fact f dot divided by f prime, seen as a vector field on the circle. So, at this stage, if our goal was merely to compute Berry phases in representations of dFs1, we would be done, because here's the Morag-Cartan form, you plug it to get the Berry phases. But we're a bit more ambitious than that, to the extent that we really want to know Berry phases in representations of Virasoro. Now, Virasoro is a central extension of dFs1, which means abstractly that it's dFs1 times a real line. You can think of this real line as the direction dual to the space of CST central charges. But what it means in practice is that when you compute the Morag-Cartan form for this group, you need to take into account one extra central entry. So as before, we can now pick a certain path in dFs1, and we ask, what's f inverse multiplying f dot, where we now think of both elements as actually belonging to the Virasoro group, the central extension of dFs1. Now, it turns out that the group operation of Virasoro is not explicitly, so in principle, I could go in front of you through the derivation of this Morag-Cartan form, but to save time, I'm obviously going to skip the computation and just tell you the result. So the result happens to be this. In the first entry, you recognize the Morag-Cartan form that we've seen on the last slide in dFs1, and then this second entry is an integral of some complicated combination of derivatives of f. Don't look too much at the details. Please just notice here in the numerator that there's a third derivative of f. This third derivative is really a remnant of the central term m cubed that you may be familiar with from the Virasoro algebra. In any case, at this stage, we know explicitly the Morag-Cartan form of the Virasoro group, which suggests that we can now plug it in our formula for Berry phases and read off some of the Berry phases we're interested in. Specifically, I'm now going to embed Virasoro in the BMS group in 3D and tell you what the corresponding Berry phases are. Now, to tell you about BMS in 3D, first I need to tell you about three-dimensional asymptotically flat gravity. So let's consider three-dimensional Minkowski spacetime. Here is a Penrose diagram of the setup, in which this radial coordinate r is such that the region where r goes to infinity is future non-infinity. It's the upper cone in the Penrose diagram. And then on that cone we have two bounding coordinates. One is the angular coordinate phi, which labels points on the celestial circle, and the other is the time coordinate u. Now, as usual by now, the game we wish to play here is one where we include gravity. That means that we put a family of metrics on such spacetime manifolds and require the metric coefficient to satisfy suitable fall-offs as r goes to infinity. The question then is, which diffeomorphisms of spacetime preserve those fall-offs? These diffeomorphisms, by definition, are the asymptotic symmetries of the system. Now, for a suitable choice of these fall-off conditions, the asymptotic symmetry group that one finds turns out to take the form written here and is known as the Bondi-Messner subgroup in 3 dimensions, BMS3 for short. Now, instead of looking at this abstract structure here, let me just tell you what it means in terms of coordinates. First, if you pick an element f here belonging to diff S1, what it does is just to deform celestial circles according to an arbitrary diffeomorphism f. So within BMS, you're allowed to deform celestial circles in any way you like. And secondly, if you pick an abelian element here, a vector field on the circle, that vector field has a component alpha, which is just a function on the circle. And what that function does is to translate the time coordinate in an arbitrary angle-dependent way. Now, in the BMS realm, those two families of transformations bear special names. Namely, the first ones are called superrotations, and the second ones are known as supertranslations. And of course, this terminology has nothing to do with supersymmetry. Instead, this prefix super just stresses the fact that this group here is an infinite dimensional extension of the Poincaré group. Indeed, Poincaré is also a symmetric product of this form, except that the left factor would be the Lorentz group, and the right factor would be the finite dimensional group of space-time translations. In any case, the reason this matters for our purposes here is that, as you can see here, there's a conformal group, really, a conformal group in one dimension, trivially. And so we can ask, does this knowledge of the Moré-Cartan form of Virasoro help us in computing Berry phases in representations of BMS? And the answer is yes. But to show you this, I first have to tell you a few words about representations of BMS in 3D. Now, the easiest way to think of those representations is, in fact, to first think about representations of Poincaré. As you know, an irreducible unitary representation of Poincaré is by definition a particle labeled by its mass and spin. Now, BMS is an extension of Poincaré, so its irreducible representations will also be particles. But these particles must contain some extra degrees of freedom here. And in fact, it's intuitively easy to guess what these degrees of freedom must be, because BMS is an asymptotic symmetry group, as opposed to the Poincaré group, which is just an isometry group. So in fact, one way to interpret this is to say that BMS representations are particles dressed with quantized boundary degrees of freedom of the gravitational field. So in short, a BMS particle is a particle dressed with quantized boundary gravitons. It may not be obvious, but in fact, if you look at the irreducible unitary representations of this type, they're also labeled uniquely by their mass and spin. And so you can really think of those BMS particles as a kind of natural generalization of Poincaré particles. In particular, from now on, I'm actually going to focus on one specific massive representation of the BMS group in 3D. And I'm going to denote the corresponding rest-frame state by this ket phi. So that state really just represents the particle sitting here in front of you at rest, possibly with some non-zero spin s. So the question we're going to ask is, when we take this rest frame state and act on it with a cyclic family of BMS transformations, does it pick up a Berry phase? And if so, which one? And specifically for simplicity, I'm going to consider a closed path that only consists of superrotations. Now, you may recall that this was the general formula for Berry phases, but now, again, I stress that we, instead of, I've been cheating because I've been telling you that we deal with diff S1, but instead, what we should really be dealing with is the Virasoro group, and when we do this, the Moré-Cartan form that must be used here is, of course, the centrally extended one.
So you're ignoring the supertrans.
Here, for now, I'm completely ignoring the supertranslations. In fact, I will not display the formula for supertranslations to save time. But there's also a non-zero Berry phase there in principle. Yes. So, focusing, as I said, on superrotations, indeed, the Moré-Cartan form you must use here is one of the Virasoro group. And if then you plug it here and then compute this expectation value using tools related to these representations, which I'm hiding under the rug, the final formula you find for the Berry phase happens to be this one. So this is a completely explicit formula for the Berry phase associated with the spin of a massive particle and with an arbitrary closed path of superrotation. So here, S is the spin of the particle, and the central charge called C here is just a Virasoro central charge. From the point of view of gravity, it's really just a parameter that specifies which action you're using, which action functional you're using to describe the gravitational field. For example, in three-dimensional Einstein gravity, this central charge vanishes, but in parity breaking theories of gravity, such as, say, topologically massive gravity, this is non-zero. In any case, the question that now remains is, can we actually provide a sort of space-time interpretation for this Berry phase, for example, in terms of precession? And to provide this interpretation, I'm now going to pick very specific choices for these curves f, instead of letting f be a completely arbitrary closed path of superrotations. So concretely, let me consider a circular path. By this, I mean one of this form, which is obtained by first acting with an arbitrary superrotation g, and then following that superrotation by a rotation at constant angular velocity omega. At the time t written here, this path actually closes, and there should be a well-defined Berry phase associated with it. So just to give you the intuition for what's going on here in red is the rest-free state from which we started. I see that not everyone sees, but sorry, it's a bit too low. Anyway, so this is the rest-free state from which we started. And then we generated the parameter space for this Berry phase by acting on this rest-free state with all possible superrotations. In doing this, we generate this infinite dimensional space, which happens to be diff S1 mod S1. Now, in terms of this parameter space, what the circular path does is the following. First, we act with the superrotation G by boosting this rest frame state to an arbitrary state with, say, non-zero velocity. And then, once we've performed this boost, we start rotating around the orbit at constant angular velocity until the path actually closes. And so the statement is that the wave function that's been carried along that path returns to itself only up to a phase which we can evaluate. So now, let me actually evaluate that phase for very specific choices of the superrotation G here. And to start with, I'm going to let G be a pure Lorentz boost.
I'm sorry, but I thought the S1 was just quotienting by that circle.
Excuse me?
You said it was the phase space was diff S1 mod S1.
Not quite the phase space, the space of parameters.
The space of
the orbit
parameters.
of supermomenta, if you will, from the point of view of representation theory.
But that S1 wasn't the... So that dotted line, I shouldn't regard that as something you quotient by?
No. This is a quotient space.
Oh, that's the quotient.
This is a quotient space, really. So,
but that dotted line that's not the circle action?
No, that's not the circle by which I am modding out. I'm modding out.
The circle you're modding out is the actual circle at infinity, right? It's the
not necessarily at infinity. Why would it? I mean, again, every point here corresponds to just one point on diff S1 mod S1. So, in other words,
but isn't the mod S1 the rigid rotations of the circle?
Yes.
Okay.
But that doesn't mean that. So perhaps your confusion here is the fact that I'm modding by this S1 doesn't mean that rotations actually act trivially on this. We can talk about it later if you want details, but it's okay. Perhaps the best intuition I can give you is forget diff S1. Think of SL2, and then SL2 has, so it's a three-dimensional group. It has a topology of, I guess, a circle times R2. And then you mod out by that circle, and then typically, say for massive quadrant orbits of SL2, the topology that you have is literally this one, a hyperboloid with rotational symmetry. But then the subgroup of rotations of SL2 still acts non-trivially on that group. So the place where you see that this is really modded out by diff S1 is the fact that the tip of this hyperbola is fixed by S1. That's where you see that you modded out by S1. But indeed, this S1 is the one of rigid rotation. Anyway, so the question now is, what if we pick specific superrotations here and read off the corresponding Berry phase? So to start with, I'm going to pick just a Lorentz boost. Now, the reason I'm calling this a Lorentz boost is because when you actually look at the way Lorentz transformations in 3 dimensions act on non-infinity, when you do this computation, the result that you find is precisely this formula here, where lambda is the rapidity of the Lorentz boost. And so the question we ask now is, if I pick this Lorentz boost, I plug it back here into the path, I plug the path into the Berry phase, and out comes the result written here. Now this, as you can probably recognize, is exactly the same formula that I showed on the second slide of the talk. In fact, it is the formula for Thomas precession. So at this stage, we conclude that these purely group theoretic Berry phases that we derived essentially on the basis of symmetry considerations have essentially been known for a century and almost routinely observed in atomic physics. But now, as I said, we can be more general than what Thomas did. So instead of restricting ourselves to Lorentz boosts, we can look at more interesting superrotations. So for the sake of this talk, when I say superboost, I will mean the same thing as a boost, except that all exponentials on the left and the right-hand side are taken to the power n, where n is some integer. From the point of view of Poincare symmetry, this transformation does not exist. It is not something you can do in pure Minkowski space. But if you look at asymptotic symmetries, and specifically BMS, this is a perfectly valid asymptotic symmetry transformation. And so you take it, you plug it in the path, you plug the path in the Berry phase, and the result that you find happens to be this one here. Now what's crucial here, as you can see, is that there's this non-zero piece involving the central charge. Now recall that the central charge is really just a parameter that we had in the action function of describing the gravitational field. So what this contribution tells you is that when you consider a particle dressed with gravitational degrees of freedom, this gravitational dressing actually contributes non-zero terms to very phases that we can at least explicitly compute. And if you even dream, you might dream of one day perhaps observing them. But in any case, there is a non-zero contribution due to gravitational dressing, which appears in potential observables. Finally, to close the talk, as Andy was asking, yes, indeed, you can also compute very phases associated with paths of super translations, but for simplicity, I'm not going to talk about this here. In any case, well, I hope to have managed to convey and share with you part of my enthusiasm for those very phases, and thank you, of course, for your attention.
So Blagoje, in the previous slide, n equals 0, minus 1, 1 should.
Sorry, what?
If little n is just 0.
Little n goes from 1 to, it's a strictly positive integer.
Yeah.
So it's 1.
So when you take it to be 0, 1, minus 1, should be.
It's not
no,
the
it's
same
just,
one.
Yeah, no, it's
the
not
same
this one.
It's not
Okay.
the same one. Or
It's
in
just
fact,
when
in
n is
fact,
one,
in fact, you can think of it that way, but you've modded. So it's related to this modding out by S1. You're modding out by n equals 0, which is why you don't see it here.
Because
I
you
mean,
see the.
I think if I trace the computation, that's where I would see it. But it's related. Sure, it is related to this n. In fact, on the Lie algebra level, this is the exponential of, I guess, ln plus l minus n in terms of functions. Yes.
Do you think you could go back to the slide where you had the general formula for the Barry phase of the
Sorry, it's going to take some time.
Yeah, just that one. So if I was considering a space-time with a black hole in it, and I set S equal to J, and I used Malcolm's C equals 24J, then those first two terms would cancel, and I'm just wondering if that's significant in any way.
So from the point of view of 3D gravity, you'd be considering, I guess, a massless PZ. I don't know if it's significant. I don't know.
I mean, 3 is more 3J, right? In
Is
3D?
it different?
It's not 4. Oh.
Sorry?
C is in 3D. More
Yeah, but no,
3.
that's not the 3 over G. That's the thing. This is the parity breaking sample plotting. In Einstein gravity, this is 0. In parity breaking theories, it's not 0. So it's really pretty much just a parameter you can fix. And I guess if you like parity, you could fix it to 0. So my short answer is, I don't think there's anything special with it. I've already had the question, does this tell you anything about black holes? To be honest, I don't think it does. At least I don't see that it does. Who knows?
I mean, the super rotational part might be more interesting, no?
You mean the super translation?
Super translation.
Yes, indeed. So yes. So the formula I didn't show is one where you also have a Barry phase associated with super translations, and there's actually a contribution proportional to this dimension full central charge of the mass, which is essentially the Planck mass. So there you actually see that there's a gravitational contribution proportional to the Planck mass to gravitational Barry phases. Yes, this you can compute, but again, for simplicity, I didn't show it here.
And you could play the same game with BTC.
Yeah. No, in fact, the original talk that I kind of converted here is one where I do it just for Virasoro representations. And you can just do it for Virasoro representations. In fact, it's much simpler for Virasoro than for BMS, technically.
Any other questions? Okay, that's fine.
Oh, no,
Sorry, Mike's mic.
No, I was just thinking, like, did you also can you do the same game like for higher dimensions as well?
So I can tell you a Barry phase associated with super translations in 4 dimensions. But since I don't know exactly what the group structure is in 4 space-time dimensions, including central extensions, possibly some sort of superrotations, I don't know how to use this kind of representation theory to tell you the Barry phase. But at least for the super translational part, I can actually write down the generalization, yes.
Okay, but it just means that some information is missing, but if you have that information, you could in principle do it.
Yes, but also without information missing, there's at least a part of the Barry phase I can write down explicitly.
Okay.
Yes.
Can I sign our speaker again? Right. I didn't make it.
Sorry.
Sorry.
That's the phone.
I didn't.